Hey world, it's Active Learning here. In today's video, we will be going over data manipulation using PyTorch. Data manipulation is a must-learn for all AI practitioners and data scientists. If you already know some basic data manipulation or you're completely new, it's okay. I will go over them step by step. I will also be discussing about their applications in deep learning. So let's get started. First, we're going to get started with the basics. These are absolutely fundamental and you have to know them for data manipulation. So in order to get started, I'm going to import PyTorch. And don't worry guys, I will link the code in the description below so you can find it there if you get stuck. I highly recommend you to follow along the video so you get some hands-on experience coding yourself. I am currently using Google Colab, so if you want to use Google Colab, you can do so as well. You can skip a lot of this setup. Okay, so first let's import PyTorch. You can do that simply by typing import torch. I'm going to run that, waiting for Google Colab to connect. Okay, so now we're connected and it is taking a while to import. Okay, now we have imported PyTorch. We can go on to the basic operations. Okay, so let's get started by understanding what a tensor is. A tensor is simply a single or multi-dimensional array of numerical values. If we only have one axis, it's called a vector. If we have two axes, it is called a matrix. And if we have more than two axes, we simply call it the kth order tensor, okay? Alright, so now we know what a tensor is, we can get started. We can first create a tensor, right? And to do that in PyTorch is very simple, and we're going to be using the basic function called arange. So let's call our let's create a vector here. Vector is a 1D tensor, right? Okay, torch.arange. Let's create let's say 12, and then we can put d type equal torch.float 32. I will explain what this is. Okay, so we just created a tensor here. Let me zoom. Alright, so we just created a tensor here, or a vector, with 12 elements. And this number here means we have 12 elements starting from 0 all the way to 11. So this number here won't be included. And here we're specifying the data type. And our data type here is a float 32. I could also do int 16, right? This will also be valid. Let's see what that returns. So now it's integers instead of float, okay? And that's what arange does. If you have worked with NumPy before, it's pretty much the same thing. Instead of torch, we might put np.arange for NumPy. Okay, now what if we want to get the size of this vector we have here? We can do x.numo or numo. This gives us, this outputs the size. So it says 12 here, that means we have 12 elements. And yeah. Okay, now I'm zoomed in all the way. It says 12. Okay. 1 second. Let me change the size. Now, what if we want to get the shape of this tensor? We can do x.shape. And this gives us torch.size 12. And yeah, if you want to access the shape, you can always do this. If we have a 2D or a matrix, you will see later on why dot shape is very important and useful. Okay, so what if I want to make this into a 3x4 matrix, right? What if I want to turn our vector into a 3x4 matrix? Well, we can do that simply. Let's call it capital X, right, for matrix. X dot reshape 3 and 4, and we can see what that gives us. Boom, see, this turns it into a 3x4 matrix, and this is also in 16. Okay, now capital letter is used to indicate that it is a matrix, and a lowercase letter is used to indicate that it is a scalar or a vector. Okay, and it's important to notice that when I did reshape here, I use 3 and 4, and 3 and 4, if you multiply them together, you get 12, which is the size of our vector originally, right? So when you're doing reshape, you have to pay really close attention and make sure that the numbers that you input into the reshape must their product must be equal to the size of your original tensor, right? Right. So if I want to do reshape 3 and 5, that won't work because our size is 12. So I must do 3 and 4. Or I could also do 2 and 6. That's also valid, right? Now we have a 2x6 matrix. Yeah, I'm going to switch it back to 3 and 4. 3x4. Okay. Now we have that done. Now, here's a very neat trick. If I want to reshape this to 3x4, I could also do x dot reshape -1 4. See, this gave us the same output. So you might be wondering, how come -1 also works? Well, this -1 here simply means that the computer has to guess this number. And since we put 4 here, it has to be 3 because our size is 12. So 12 divided by 4 gives us 3. So the computer automatically assumes that this number here is 3. And this works the other way around. If we wanted to put this as 3 and this as -1, that also works. And what if we want to create a tensors initialized with all zeros or ones, right? Practitioners, AI practitioners often need to work with tensors initialized with all zeros or ones, right? This is really important. So you can do torch.zeros, and I can give it a shape in here. Let's say 2 by 3 by 4. This gives me a 3D vector, a 3-dimensional tensor here, right? It's all initialized with zeros. I can also give another value, torch.zeros. I can do it 3 by 4, right? That will also work. Now, what if I want to give it all ones instead of zeros, right? We can do torch.ones 3 by 4. See, the syntax is very simple and very intuitive, right? Now, what if I wanted to initialize them with random numbers instead of zeros or ones, right? This part is actually very important because random numbers are extremely useful, especially when we want to initialize the weights of a neural network with random numbers. This is because randomizing the weights can allow us to break the symmetry in the network, which makes the process and chances of finding the global minimum easier, right? If you have watched my video on deep learning, you know that we want to try to find the global minima instead of the local minima, right? So if we didn't use random initialization, all the neurons in the neural network would perform the same computation and produce the same output, resulting in poor performance. Additionally, starting with random weights can also prevent network from getting stuck in a poor local minimum during training, right? So that's why we want to initialize with random variables. So this is why you want to learn this closely, right? You can simply just do torch.random 3 and 4, right? This creates random numbers they grab from the Gaussian distribution. It's 3 by 4, okay. And yeah, you want to keep this in mind because it's super useful. Okay, now what if I wanted to create a tensor on my own without using torch.zeros or a range or ones or random? Well, we can just simply do torch.tensor, right? This creates a tensor, and we can do 1, 2, 3, 4. This gives us a vector here, right? We can also do torch.tensor. We can give it a matrix, right? We can do 1, 2, 3, 4, and then we can give it 3, 5, 6, 7, 8, right? This will also work. These are all tensors, right? Okay. Now we're done with the basics. We can move on to index and slicing. Okay. So let's grab our matrix X again, just to remember what we have. We have these values for our matrix X. And what if I wanted to grab the last row here? What if I wanted to grab 8, 9, 10, and 11? How can I do that? Well, you can simply slice through tensors just like you would slice through a simple Python list or a NumPy array, right? You can do x -1, right? This gives you the last row here, and if I wanted to grab the second row here, it would be x1, right? This will give me the second row here. This is also a tensor, right? Okay. Now, you might be wondering, why is this the second? Why does this give us the second row if we only put 1 here? Well, remember that tensors are zero index based, just like Python list. So 0, 1, 2, 3, this is index 0. 4, 5, 6, 7, this is index 1. 8, 9, 10, 11, this is index 2 here. So that is why. Okay, now what if I wanted to grab a range of values, right? What if I wanted to grab the last 2 rows, right? 4, 5, 6, 7, 8, 9, 10, 11. Well, I can simply do just like slicing in Python list. We can do x, and then we want the last 2 rows, so it will be everything after 1. After 1, and then we want everything. So let me explain to you the syntax here. This means that we're starting at row 1 and we're taking everything after it. This means let me show you the syntax here. So it's start and non-inclusive, right? So it's from 1 to whatever number you want to end at. But since we're not providing a number to end at, it will just simply take every row after row 1 as well. And here we're taking all the columns because we want the rows after 2. But yeah, that will mean every column, right? So let's see what this gives us, right? It gives us another matrix containing the second and third row. Okay, now we got that out of the way. We can also specify certain values we want, right? So let's see our matrix X again, just to remind ourselves. And if I wanted to change, let's say this value here, 5, right? If I wanted to change this value, I can do that just like I would do it in a Python list, but it's a little bit different. So I wanted to give it 1 and 1, right? This gives me 5, which is what we want, right? So how do we get this value? Well, this means row 1, we're in the first row, and the first column, right? It's 0 index space, so this is row 1, and this is row 1, this is column 1, right? If I wanted to grab 8, it will be 2, 0, right? That will give me 8. Okay, but what if we wanted to change this 8 value here? I can just set it to, let's say, 12, right? Now, let's see our X matrix again. See, this value is now changed to 12. Boom, okay. Now, what if I wanted to change a range of numbers to 12, right? I can do, let's say x2 equal 12. So what this is doing, it's taking everything before the third row, right? So this means that it's not including this row here. It's non-inclusive. So 0, 1, 2, this row is excluded, and it's taking everything before that. And we're taking all the columns, right? We want all the columns here, and we want to set them to 12. So let's see what that gives us. Boom. All these values here are now changed to 12. Okay. Now we got that out of the way. I think we're done with indexing and slicing, right? I will share the code below, so don't worry if you have any troubles or you're not following along quite fast enough. Okay. Some of the most useful operations are the element-wise operations, right? So these apply a standard scalar operation to each element of a tensor. So what do I mean by that? Let's remind ourselves of our vector x here. So we have this vector x, it's filled with some values, okay? Now, what if I wanted to apply e of x to all elements in the tensor, right? E here is basically the Euler's number. It's a constant, okay? So how do I apply that? Well, PyTorch has this cool feature called torch.expo, and we can simply put x here. And you might be wondering, what is this stuff? Well, it's simply e raised to the x, right? In this case, x is each value element-wise, right? So we're applying x this to every value, every element in our vector here, right? But we can also apply binary scalar operations. So what do I mean by binary scalar operations? So if we're given two vectors u and v of the same shape, right? So let's say I have u equal torch dot tensor 1, 2, 3, 4, and I have v equal torch dot tensor 5, 6, 7, 8, right? So if these two have the same shape, right? If we give them the same shape, and we also provide a binary operator, let's call it function f, we can provide a new vector c where we plug u and v into the binary operator f, right? So let's see what I mean by that. Well, c equals u plus v. And this will apply element-wise, right? So we're adding 1 to 5, 2 to 6, 3 to 7, 4 to 8, right? We're adding them together element-wise, right? So that's how you can combine the values of two tensors into a single tensor, okay? Now you can also do c equal u times v, right? So these are all these are all scalar operations you can apply, right? Multiply, add, you can also do subtract, c equal u minus v, and let's see, c. See, now we are subtracting them from each other, okay? Very, very cool stuff. And divide also works if you want to try that. Now, what if we want to concatenate multiple tensors together, like stacking them end to end to form a large tensor, right? We just need a list of tensors and tell the computer which axis to concatenate, right? So let's see how we can do that. We can do, let's say we're creating a tensor here. Let's apply what we have learned so far. Let's use a range and 12 d type equal torch dot float 32 dot reshape. So what this is doing, it is generating 12 values from 0 to 11, right? 0, 1, 2, 3, 4, all the way up to 11. And they're of data type 32. And we're reshaping it to 3 by 4 instead of a vector, right? Now it's a matrix after we apply dot reshape 3 by 4. Now I want another matrix to be, let's create this on our own, all right? Let's see, let's say 2.1, 4, 3, and we can create another row. Oops, I actually forgot something here. You wanted 2 brackets here if you have a 2D matrix, right? Okay, now I can also have 1, 2, 3, 4, and I can have 4, 3, 2, 1, right? Very cool. It's giving me an error, even though it shouldn't be. It's not closed. Oops, I missed a comma here. All right. So this is another cool thing. Let's first see x and y, right? Display x, display y. You notice that these values are all float values, right? Well, how did this happen? Well, because simply we have one value here that's a float. Now this assumes that every other values are also float values, right? So we have x here, right? And you see what we get? We get every value from 0 to 11, and we reshaped it to 3 by 4. All right, cool. So let's see how concatenation works, right? If I wanted to stack something vertically, right, I can do concat horizontally, horizontal stack, let's call it that, equal to torch dot cat. This allows us to concatenate, and I will provide it with x and y, and axis equal 1. So let's see what this does first. Display concat horizontal stack. Boom, it concatenated both of these horizontally, right? When you see axis equal 1, just think horizontally, right? In the x direction. So when you concatenate x and y, we're concatenating them, combining them, stacking them in the x direction. Okay, so how do we do the y direction then? How do we concat them vertically, right? Concat vertical stack. We can also use torch.cat. This allows us to concatenate them, and we provide it with x and y. And then instead of axis equal 1, we can do axis equals 0. And let's display that vertical stack. Boom. Now this is concatenated vertically, right? And instead of axis here, you could also use dim. That also works, right? See, dim also works, but I personally prefer axis. You can think of them as the x-axis and the y-axis, right? It's really simple to memorize. Okay, so now let's talk about application-wise, right? Why is concatenation useful? Well, in a neural network, for example, concatenating multiple feature maps along the channel dimension can allow for increased model capacity and the ability to learn more complex representations of the input data. And additionally, concatenating multiple input sequences or feature vectors can be useful for tasks such as machine translation or image captioning, right? So if you didn't catch all of that, just know that concatenation is very useful and you will use it a lot. Okay. Now, how can we compare to binary tensor through logical statements, right? Well, it's just like in normal Python. You can do x equal y, equals equals. This means that we're comparing if they're equal. And this returns a matrix of Boolean values, right? So false. This one's true. You might be wondering why. Well, let's go back to our x and y, right? So both of these are 1 in our x matrix and our y matrix. That's why it's true here. So this is how you can compare it to matrix to logical operations. You can also do x greater y, and it will return true if this specific value here is greater than the specific value here for y, right? Now, let's see what other cool tricks we can do. What if we wanted to take the sum of all the values in a tensor? We can simply do x.sum. See, this returns a scalar value here, which is 66, and that's the sum of all the values in our x matrix. Boom. Okay, now we are finished with the operations you can perform. I think these are all very important. Actually, we're going over some of the most important stuff today. Okay. Now let's move on to broadcasting, right? Okay, so what if we want to take the sum of two tensors that have different shapes, right? Up here in operations, we only worked with matrices that have the same shape, right? This is 3×4. This is also 3×4, right? But what if I wanted to do something else, right? What if I have a tensor u equal torch dot ran, let's say 2×3, and I have another tensor where it's 3×1, right? Which means it's a vector. So how do I deal with this, right? Let's see them first. Oh yeah, actually another note here. If you're using random here, we might get different values, right? Because it's providing random number. If we wanted to get the same value, we could set the seed, but in this case it's not necessary, right? Okay. So anyways, so here's our matrix U, and this is our vector V. So how can we take the sum here element wise, right? That may seem very difficult. Well, this is where it's very cool. We're talking about something called broadcasting here. So let's say C equal U plus V. Let's see what C is. Boom, that actually worked. So you might be wondering, how did that work? Well, broadcasting basically expanded this to the same shape as this larger tensor here. So now this value here is added to that and that. So that's how we get these values here. This value is added to that, and this value added to that, this value added to that, and that. Okay, that's how we get these values here. Okay, so PyTorch can broadcast tensor V along the first dimension to match the shape of tensor U, and this allows us to perform an operation such as addition between the two tensors, right? And notice how the resulting tensor has the same shape as U, right? Okay, now we're going to talk about something called saving memory. This is very important if you want to create your own machine learning model, right? So let's display U and V again, our two tensors. This one's a matrix, this one's a vector. Okay. Now, let's see where they're stored up in memory, right? Let's say before ID equal ID U. Now, let's perform some operations. We can add them together. We set U to U plus V, right? And then we can get there after ID equal ID U. We're still getting ID U here. This is before operation. This is after the operation. Now let's see if before ID is equal to after ID, right? Oh no, it says false. So how did this happen? Well, you have to notice how the memory location changes when we perform the element-wise binary operations. This means that it will allocate new memory to store the result of u plus v. And this can be very bad because number one, we're allocating memory unnecessarily all the time, right? And two, this can lead to memory leak, right? So how do we fix this? Well, fortunately, it's actually very simple to fix. So let's do that again before ID equals ID u. And now, how do we fix it? Well, we simply, instead of u equals u plus v, we can just do plus equal v. This both saves us and also saves us a lot of time, right? Now let's get the after ID and let's see if they're equal to each other, right? Boom, they're equal. And another thing you can do is actually, let me copy that. Copy cell, paste. Okay, now another thing we can do is instead of this, I can also do u equals u plus v. This is also true, right? This will basically slice through the entire tensor here, and that will also work. But of course, this is a lot simpler and saves us a lot of time in typing as well. Okay, cool. We're almost done here. Now let's talk about how we can convert to other Python objects, right? So let's see our tensor u again. This is a tensor. How can we convert this to a NumPy array? Well, we can do, let's set matrix A equals u dot NumPy. Now let's see A. Boom, now it's a NumPy array. Simple as that, right? We just gotta type dot NumPy. Now, how do we convert it back from a NumPy array? Well, we can do torch dot from NumPy A. And now let's see B. This is a tensor again. Now if we want to check their shape, we can do type A, type B. See, one's a NumPy array, the other one's a tensor. Very cool. So now I have provided some exercises that we can work through to solidify our knowledge, right? So let me paste that here. Okay. Boom, boom, boom. Okay, so this is problem 1, problem 2, problem 5, problem 6, problem 7, and problem 8. Alright. So, yeah, after you watched everything, do these exercises. And once you're done with them, come back and we'll work through them together. All right. So, take a 5-minute break, do these exercises afterwards, and come back. Okay. So, hopefully, you gave it a try. I really hope you did because that's how you can get some hands on experience while making sure that you actually learn something, right? Okay. So, let's go through number 1. Number 1, it says create a tensor of shape 4×3 filled with random values and then extract the second column of the tensor. So how do we do that? Well, let's say our matrix A is equal to torch.random 4×3. This gives us a 4×3 matrix. Now we can display A and we can grab the second column. So we want to do some slicing here, right? Slicing, cool. Now see how I did that? So I'm basically taking all the rows, right? We want all the rows, and we're taking the the first column, right? Or in this case, since it's index based, zero index based, right? So the first column. So we're taking all the row and the first column. This gives us the second column, right? One based. All right. Now let's do number 2. Create a tensor field with zeros. Well, this is really easy, right? A equal torch dot zeros 4 by 3, and let's see A here. This is a tensor field with zeros. Cool. All right. Now let's say we wanted to do number 3 here. Create a tensor field with ones. Easy torch dot ones 4 by 3. Okay. Right. The syntax is very easy to memorize. Just type torch and dot ones. Right. Okay. Now let's do number 4. Create 2 tensors A and B, fill with random integers, and then store their element-wise sum into a new tensor C. Okay. Number 4 here. So equals torch dot random 4 by 3. B equals torch dot random 4 by 3. And C equals A plus B, right? This gives us their element-wise sum. All right, very cool. Okay, I ran my mouse there. All right, let's see. Okay, that works. Now let's do number 5. Create a tensor with 3 dimensions. Well, this is also very easy. We just have to do. Actually, let's do something cool here. Let's apply what we have learned. A equals torch dot A range, right? Let's use some A range cool tricks. And we can do reshape 3, 3, 3, right? Notice that their product is 27, right? It has to be equals to 27. And this is 3D. Now let's see A. Right, it's a 3D tensor here. We could have also done actually, let me do that in the same cell here. B equals torch dot tensor 1, 2, 3, 4, 5, 6. Right, this will also work. Right, this is also a 3D tensor here. Okay, now let's move on to number 6. Create 2 tensors A and B with different shapes and use broadcasting to obtain their element-wise sum. Okay, so let's do number 6 here. We can say 6. Let's initialize torch A with torch.random 2 by 3. Let's give it a data type of torch.float 32. Okay, and then we can give B a single value of 2, right? This is also float 32 here. All right, now let's display A and display B. Let's see what we get. Right, these are our values. Now let's display A plus B. So we're simply adding to every element here, right? We're adding this element to every element here, and this is what we get. Very cool. Now let's move on to number 7. Compare 2 tensors using logical statements. Okay. I didn't specify what specific logical statement, but let's just do all of them, because why not? All right. A equals B, display A greater B, display A less than B, display A less than equal B, display A greater equal B. Boom. All right. So that's just comparing all of them. These are the logical operations you can perform here. Okay. Now let's move on to number 8 here. Create 2 tensors of shape 3 by 4 and concatenate them horizontally and vertically. All right, easy. We can do number 8, A equals torch dot random 3 by 4, B equals torch dot random 3 by 4. This is just taking random numbers from the Gaussian distribution, and we can display torch dot cat. This concatenates A and B, and we're gonna provide an axis. So since we're doing horizontal, we provide it with axis equal 1, and let's do vertical now. Axis equals 0. All right, so boom, that's all. And yeah, that's it for this video. Everything you learned today are super important if you want to become a deep learning practitioner or a machine learning practitioner. These are all super useful stuff. And if you wanted to find the code, it's going to be in the comments or description below. And yeah, if you guys found this video helpful, please leave a like and subscribe. And if you have any questions, please ask them down in the comments below. I will clarify all of them for you. And yeah, if you're stuck, you can also ask ChatGPT. It's a great tool, honestly. Yeah, so see you guys next time. Bye.